This is the story of three cylinders, A, B, and C. If you focus in on A, you can see that A has a radius of 2 units and a height of 4 units. And if you look at B, we have a radius of 4 units and a height of 8 units. And A and B look very much alike, and they are proportional, both in appearance and in measurements. We multiplied the height by the same ratio, namely 2, as we did the radius to go from cylinder A to cylinder B. The radius is twice as long in B as it is in A, and the height is twice as tall in B as it is in A. So these shapes are similar because their parts fall in the same ratio. If we look over here at C, C has the same 4-unit radius that B does, but its height is 18. It's much taller proportionally than it is wide when compared to A and B. C looks more like a Celsius can than A and B do. So C is not similar to A and B because its parts do not fall in the same ratio as A and B do. So let's just get rid of C here. Goodbye, cylinder C. So we're going to concentrate on A and B here. So the ratio of A's parts to B's parts is 1 to 2. 1 to 2. There it is right there. It's linear pieces. Its radius, its height, those linear measurements. If we look at the lateral areas of these two shapes, and we do the math on it, lateral area for A is going to be, it's going to wind up being 16 pi. For B, it's going to wind up, when we do that calculation, it's going to be 64 pi. So when we multiply, or actually when we compare those as ratios, 16 pi over 64 pi, that's going to simplify to a 1 to 4 ratio. We would get the same result from surface area if we did that. Volume, things are going to get even fishier. The volume of cylinder A is going to wind up being 16 pi, and the volume of cylinder B winds up being 128 pi. If we put those in ratio form here, we do the division on those, we wind up getting a 1 to 8 ratio. So we can see that while the linear measurements of cylinder A and cylinder B fall into a 1 to 2 ratio, the lateral areas of those two fall into a 1 to 4 ratio, and the volumes of those two fall into a 1 to 8. We can also think of 4 as 2 squared. And of course, 1 is also 1 squared. Volume, 1 cubed to 2 cubed. So what we see happening is that the ratio of the areas is the square of the ratio of the linear measurements, and the ratio of the volumes of these two similar cylinders is the cube of the ratio of the linear measurements. This is noteworthy, and it leads us to this great chart here where given either the linear measurements, the areas, or the volume of two similar 3D figures, we can find the ratios of the others. So if we know the ratio, we've already seen that if we know the linear ratio, we can square it to find the ratio of the areas, and we can cube it to find the ratio of the volumes. But let's say we were given two similar figures and their volumes. We could use that ratio cube root it to undo the cubing to find the ratio of their linear measurements. If we knew the areas, we could set them into ratio form and square root that ratio to get the ratio of the linear measurements.